Hello and welcome to the latest session for our OptiSystem software. My name is Joshua Donald and I'm the Photonics Applications Engineer here at OptiWave, and I'll be assisting your host Ahmed Attia. The webinar seminar today will focus on optical communication transmission simulation using the GN model. We will also have a Q&A period at the end of our hour-long presentation, so feel free to go ahead and use the questions panel and type in any questions you have in there, and we will try to answer all the questions before the end of the session. Now, over in the handout section, you'll find the PDF that'll be used in the presentation, so feel free to download that at any time. And lastly, we will be recording this webinar and emailing the link to everyone an hour after the broadcast. With that said, let's get the webinar underway. I would like to introduce your host, our Director of Optical Systems, Ahmed Attia.
Hello, everyone. Today's webinar would be about using the GN model in simulating optical signal transmission over optical fiber. And the webinar today will include an introduction. Then we're going to talk about the theory behind the GN model. And we're going to talk about the GN model component in OptiSystem and talks about the features of the component, the parameters set, how to set the parameters in the component. And then we're going to show you what kind of results you expect from this component. We show you the live demonstration, and at the end, we're going to have a small session for question and answer. Optical signal transmission in fibers is usually modeled using the nonlinear Schrodinger equation shown in here. This equation addresses the physical characteristics of the optical fiber, including the attenuation, the dispersion, which is in this equation. We have the group velocity dispersion and the third order dispersion. Also, there is in the equation here, we have the nonlinear effects due to self-phase modulation. The terms here is for self-steepening, and this term related to the stimulated Raman scattering. In OptiSystem, we address all the nonlinear effects in the fiber, including the self-phase modulation, cross-phase modulation, four-wave mixing, stimulated Brillouin scattering, stimulated Raman scattering, in addition to the self-steepening. The equation, the nonlinear Schrodinger equation, is solved using the split-step Fourier method. And depending on the complexity of the transmission system and the number of wavelengths or channels used and the reach, in addition to the modulation scheme used, this calculation could take many hours. And a solution to minimize this time of calculation is addressed using the GN model. In this slide here, we show you the block diagram of the transmission system, which you can be modeled and simulated using the GN model, where we have N channels, DWDM channels, it modulated using advanced modulation scheme such as MQAM, could be 16, 64, whatever the QAM modulation scheme, determined by the number of bits per symbol. And PSK, MPSK, the same thing as you can have control the number of bits per symbol. These WDM channels after modulation are multiplexed and transmitted over a multispan fiber, and each span has a length of L, then amplified after by an EDFA. Then the channels after transmission at the receiver and demultiplex goes through a DSP, digital signal processing component, and then received using a coherent receiver and passed into the decision circuitry to determine the performance of the transmission system. Now, the GN model do this kind of calculation in very fast way, and that's the advantage of using it. And today's webinar talking about that process. So, what is the GN model? The GN model calculates mainly the nonlinear interference in the transmission link, and the calculation is actually very, very fast, a few seconds, where we can simulate multispan, the DWDM optical transmission, as we said earlier. The GN model has a very high accuracy, and it can display results as Osin out of the system versus transmitted power, bit error rate versus received power, and maximum reach, system reach versus transmitted power. The GN model has a few assumptions which used in the calculation and the model, and these assumptions are necessary to achieve very good accuracy. Now, if some of these assumptions is not met, there would be some kind of discrepancies between the real system and the actual simulations. So the first assumption is here, we assume that the transmission link is transparent, which means that each span is completely compensated using in terms of attenuation, in terms of an EDFA. So the EDFA would amplify or compensate for losses of the fiber. The second assumption here is we assume that the amplification is lumped amplification. There is no distributed amplification in the model. However, the model can accommodate distributed amplification. At this stage is not added in the component at OptiSystem. And the transmission link also assume that the system is, or the link is homogeneous, which means all the channels have the same bandwidth and wavelength spacing. Here you see in this figure an inhomogeneous link where each channel has a different bandwidth, and that cannot be applied using the GN model. There's other assumptions in the analysis of the GN model is the spans has to be identical. So the length, for example, for each span is supposed to be the same length. So for example, if you assume 100 kilometer between span and span, it has to be equal. The other thing is you can assume that the link is doesn't suffer from ISI or linear crosstalk, because we have a DSP chip at the receiver, and this DSP has a match filter to compensate for any dispersion or any or crosstalks between channels. The other assumption here is the TX and RX pairs are having no impairments, which relates to the data acquisition or digital analog converters, amplifiers, op-amps, and all these things, which is typically very difficult to predict and in the systems. And the last assumption here is the nonlinearity in the link is relatively low to moderate nonlinear regime, and which is usually this is the regimes used in optical transmission system in actual systems. Okay, some background here. GN model is handles the transmission system that limited, as we see as we saw in the block diagram. We have EDFA after each span. So the EDFA has noise coming due to the amplified spontaneous emission. So all the noises due to spontaneous emission are modeled in the GN model here. And then the other part of it, which is related to the nonlinear interference, which is the main kind of modeling used in the GN model. The nonlinear noise interference and the ASE noise, they in this model are added based on the assumption that their statistical behavior are Gaussian independent. And we're going to show you next the assumption based on what in the next slide. Once we assume that the noises, the ASE noise and nonlinear interference noises are added, then the calculation of the OSNR parameter of the system is easily done using the relationship of the power of the channel divided by the noise created by the ASE and the nonlinear interference. The main cause or main assumption about the channels are added, or the nonlinear interference of the ASE and nonlinear interference are added due to their behavior, is coming from this picture here, which is published in 2012 by a group in Italy. And the channel here, the green line here shows 17 Nyquist WDM channels, each one of them modulated at 32 gigabaud. And the blue line here, it shows the power spectral density of the nonlinear interference noise generated by the fiber. And if you look at the assumption here is we're going to assume that each channel in here, which are, we have 17 under the green line, each of them has almost flat nonlinear interference. So the assumption here is we have Gaussian additive locally white Gaussian noise. And this, if the assumption that it's flat for each channel, which is not really exactly, it causes about 4% decrease in the system theoretical maximum reach prediction. The paper here by this group, they have detailed analysis about the effects of variation from the assumptions, which we showed you earlier. And if you wanted to go to, you may refer to it. At the end also of this presentation, there is a few references from this group about this work. Okay, so now we're going to talk about the model itself, the theory behind it, and the general equation used for the GN model. As you see here, it's a very complicated equation which describes the Bauer spectral density of the nonlinear interference in the system of multi-DWDM channels modulated as QAM or MQAM or MPSK. This Bauer spectral density of the noise depends on the Bauer spectral density of the overall DWDM channels transmitted, as you see here in this term. And the other terms in this equation here are created based on assuming the third order dispersion equal to 0. And this is possible for systems, transmission system with the group velocity dispersion above 2 picoseconds square per kilometer. Now, in the other parameters in this equation, we have the fiber nonlinear coefficients, the length of the span, each span. This is the group velocity dispersion, and this is the number of span in the equation. Now, this equation it's very difficult to solve it right as is. So what's happened is there is depends on a few cases. We're gonna discuss them later on. Depends on these cases, the equations will be simplified and possible to solve it. Okay, so the nonlinear interference noise can be added in each span coherently or incoherently. So if we have a multispan transmission system, the noise due to nonlinearity can be added up incoherently or coherently. Depends on a question we're going to show it to you next. And this, based on the equation, the general formula of the Bauer spectral density of the interference, nonlinear interference Bauer spectral density would be calculated. Now, if the nonlinear interference in each span is added incoherently, this is the equation for the general Bauer spectral density of the system, which is number of span times the Bauer spectral density of the first span, basically. Now, if the nonlinear interference noise is added coherently, which means you have phase matching between each span in terms of noise, the equation would be a bit different here. As you can see, instead of number of spans, we have 1 plus epsilon, and epsilon is equal to 0 for incoherent contribution. And for perfect phase matching between the nonlinear interference in each span, we're going to have epsilon equals 1. And in other cases, it's going to be between 0 and 1. The equation for calculating the epsilon is using this equation, which depends on the parameter which is called LA effective asymptotic effective length, which is related to 1 over 2 alpha, where alpha is the attenuation of the fiber. We know the effective length is typically given with this equation, 1 over minus E minus 2 alpha LS over 2L. Okay, so in the link, basically what we do, we calculate the L effective, we calculate epsilon, we know the system with the noise is going to be added coherently or incoherently, and based on that, we will be able to calculate the Bauer spectral density of the transmission link. And then now BWDM here is the overall bandwidth of the channels, which is number of channels times the bandwidth of each channel. Now, there is these cases, 4 cases here. It's simplifying the calculation of the general equation of the GN model. and based on if we have single span or multi-span, if the channels are Nyquist WDM channels or non-Nyquist WDM channels. Now, in terms of the definition of Nyquist, is when the channel bandwidth equals the channel baud rate, then we call the channel is Nyquist channel. Now, ideal Nyquist channel, we can assume that the bandwidth is flat at the top. There is no kind of curvature or at the sides of the spectrum of the channel. Now, the case one is also applied for cases where we have span loss over or equal 7 dB, which is for single mode fiber, it's like about 35 kilometers. So in this assumption, like the span length would be more than 35 kilometers. If it is less, the accuracy would be is not the calculation would not be that accurate. However, you can do the calculation still. The WDM channels has to be more than 25 gigahertz. Now, if you use these two assumptions, then because we have only single span right now, so we have only one Bauer spectral density at f equal to 0, and in that equation, the Bauer spectral density can be approximated using this equation related to the sine hyperbolic inverse of the term here. All these parameters is well known and can calculate it as we saw earlier. Now, the second case which we address in the GN model is the multispan Nyquist WDM. So still we have Nyquist WDM channels, but we have now multispan. So now number of spans you can have as many as you design or as you require in your transmission system. However, the span losses, again, this is to get accurate calculation of the GN model. And then in this scenario, we will have the overall Bauer spectral density of the nonlinear interference noise in the system as n number of spans to the power of 1 plus epsilon. And epsilon we calculated using the equation which we saw earlier. Now, in that scenario, the first nonlinear interference at f equal to 0 would be given through this equation. Now, the third case in the GN model is the case where we have single span and a non-Nyquist WDM transmission. So again, then the channel bandwidth doesn't equal the baud rate in this case. So we have two cases here. First case is when we have span loss is more than 7 dB, so over 35 kilometer of single mode fiber at 0.2 dB per kilometer loss. And then we have channel baud rate is more than 10 gigabaud. And we assume here that beta 2 is 3 picoseconds square per kilometer. If you remember, we said that the equations, which is the GN model, we assume the third order dispersion for cases where we have group velocity dispersion more than or equal to. So this is just to satisfy that condition. In this scenario, when we have single span and non-Nyquist WDM transmission, then the at f equal to 0, the nonlinear interference Bauer spectral density would be given through this equation. And the delta f here in this equation will be given as the channel separation between the wavelengths. Now, the second case for the single span and non-Nyquist WDM is when we have the ratio between the channel bandwidth and the DWDM channel spacing is more than 0.25, and the channel rate is over 28 gigabaud. The beta 2 over 4 picoseconds square per kilometer. In that scenario, the equation is a bit different. It's simplification of it. Again, all of this simplification is a result of the original equation shown earlier. And based on the assumptions, some terms would be simplified to this final equation of the Bauer spectral density at f equal to 0. The last case here is multispan and non-Nyquist WDM transmission. And in this case, we have same thing, is span loss has to be more than 7 dB, more than 35 kilometer. And the ratio between the channel bandwidth and DWDM is more than 0.25. channel rate is 28, and beta 2 is group velocity dispersion is more than 4 picosecond square per kilometer. As you saw, this conditions is similar to the last case, although but the last case was on for single span. Here we have for multi-span, and the equation we're going to use the overall nonlinear interference Bauer spectral density of the transmission system is given by this ratio, and for epsilon is given by this formula, which is depends on the asymptotic effective length and the channel bandwidth, number of channels, and the span length. The delta F here is the separation between the DWDM channels. Now, when you plug this equation and find the epsilon, you can find the GNL0 here, and then eventually you can calculate the first at F0, the GNL, the nonlinear interference noise Bauer spectral density using this equation. Now, once we calculate the Bauer spectral density, we should be able to calculate the Bauer from the bandwidth of the noise. The optical noise bandwidth is given by Bn, and the channel baud rate is Rs in this equation. So we can calculate the optical spectral noise ratio from the electrical signal to noise ratio using this relationship. And the electrical signal to noise ratio is the Bauer of the channel over the noise coming from the EDFA and from the nonlinear interference. If you simplify the equation and plug in this equation here, you can simplify to this here, and then final equation would be the signal to noise ratio electrical is the Bauer spectral density of the overall DWDM signals divided by the Bauer spectral density of the ASE and the Bauer spectral density of NL interference at F equal to 0. So, and this is the equations. Earlier we did the calculation of this part, and this part is coming from the EDFA noise figure basically. Now in this section here, we're gonna start talking about the component in OptiSystem 16, because we released OptiSystem 16.1 with a C++ component. Now this C++ component, it's not the final component for the GN model. We just release it to introduce the model to users and hopefully get some feedback about the component and about any requirements from the customers. So in this component, the C++ components is designed to accommodate this different 4 cases which we looked at it for the transmission system, which solved by the GN model. In this example here, it's created in OptiSystem examples, which you can see in under OptiSystem samples, 16.1 samples, and under advanced modulation. So if you go to advanced modulation systems, then you can go to GN model, and in GN model you have this example, which is GN model implementation. And in GN model implementation, if you double click on it, you're gonna see this example in here. And this example, to be able to view the results which we mentioned about, you can look at OSNR, at PAR, and maximum transmission length. You need at this moment a GNU plot software. Now to download it, which is free, you can download it, and once you download it, you should be able to view the results of the calculation. The C++ component right now, if you double click on it and you look at the parameters which user can enter for the transmission system, you can see here, you can look at the span length. So this is the span length of the fiber transmission length. Then you can set up the fiber attenuation as we look at some of the main parameters in the equations. You can set up the nonlinear the effective area of the fiber and the nonlinear refractive index. From both these parameters, you can calculate the nonlinear coefficient of the fiber, which is gamma. Now you can set up the dispersion of the fiber, and then from it you can calculate the group velocity dispersion. You set up the channel spacing. So the channel spacing here, by the way, you can go into set up from gigahertz, like here right now, set up at 50 gigahertz, the channel spacing. You can control the channel bandwidth. Same scenario, you can control, scroll between the different units, which is comfortable for you. Now, channel bandwidth is 32 gigahertz. Here we assume that the EDFA has a 5.5 dB noise figure. So these parameters, you can set them up in the calculation. Here, noise bandwidth, which is the electrical noise bandwidth, to be used in the calculation for the ASE noise. And here the concept of calculation. So we have two models here, coherent, as we explained before, and incoherent. So if you calculate coherent or incoherent, you choose the way you wanted to calculate. You can calculate single point or multi points in the calculation. This is especially for the bit error rate calculation. Now, the bit error rate calculation, if you wanted to scan through a range of power levels. So for example, here we scan from a maximum power level of 5 dBm to minus 14 dBm. If you click, you don't select the single point, which means you're going to calculate over the range here. If you select single point, then basically you're going to calculate over only one single point, which is the power per channel here. So the power per channel here set at minus 10 dBm. If you don't select it, you're going to scroll through the values from 5 to minus 14 in the analysis. Now, this is the step size. This is the calculation of the power between minimum and maximum. Every step would be 0.2 dB in this setup. Then the wavelength here, the calculation, all these parameters set up at certain wavelength, you can set it up. Now, in modulation type here, as we mentioned earlier, we can do M-QAM. So you can do 16 QAM, 4 QAM, 16 QAM, 32, 64, 256, all the QAM possible. And the same thing for MBSK. So if how to set up the type of QAM, you go here into bits per symbol. So here it's set at 4 bits per symbol, which means the M-QAM is 16 QAM. And then this is number of channels here. The number of channels, you can enter the DWDM number of channels, and that will control, if you remember, the WDM bandwidth of this overall system. Now, this is number of span here. It's 20 spans, for example. So 20 times 50 is around 1,000 kilometers, this system. The number of channels in the simulation, it's recommended by the authors who did this the derivation of the equations, that the number of channels has to be odd. So if you have a certain number of channels, has to be an odd number in here. Now, once you set up all these parameters, then you can press OK and then calculate the model. As you can see here, the calculation is very, very fast. Now, the calculation, you have different figures, as you see here. So the first figure is the calculation of OSNR versus bit transmission. And as you remember here, we took a power from 5 dBm to minus 14 dBm. The range of calculation with every step is 0.2. So this is the, let's say, for example, the maximum OSNR, we can get around 24 dB at around minus 4 dBm transmitted power. The second graph we can get is as a result of this component, is the maximum reach and the maximum reach versus transmitted power. Now, the transmitted power and received power, by the way, they are equal because we have, if you remember, the link condition here is the attenuation is completely compensated by the EDFA. So whatever you transmit, you just receive. And in this graph here, you have the maximum transmission length. We can go up to, let's say, 24 or 2300 kilometers if you transmit power at minus 4 dBm. And the last graph, which is available on this component, is BAR versus B transmission. So this is the log BAR versus the B received or B transmitted is exactly the same. So if you go, let's go back again to the presentation. As you see here in OptiSystem 16.1, which was released, we have designed developed the GN model in a C++ component. But in the next release, we expect to have the GN model, which is already done. We're going to release it in release 17.0. The GN model component, which will be placed in under the fiber, as in this here. I'm going to show it to you. Just give me a second, please. Okay, so in this component, we are placing it under default optical fibers library. So the GN model component, you just drag it here, and then when you double click on it, you kind of have the same parameter which were set in the C++ component. Now it's organized in an OptiSystem component. So you have the main tab here where you describe the fiber, and then the second tab here you describe the channels, the DWM channels, and then the modulation scheme and the simulation where you control. So this component, again, it will be available in OptiSystem 17, which is going to be released in the next few months. Okay, so the last thing here, before we go to the question period, we're going to talk about the references used in the calculation of the models. So here it's about 5 references from the same group in Italy, where they used to develop the GN model technology and the simulation tool. With this, I conclude the presentation, and now I'm gonna take any question. Thanks for listening.
Thank you for tuning into this live webinar. We will be emailing a link of the webinar recording to everyone an hour after the broadcast. Any questions submitted during the webinar that we haven't had a chance to answer will be answered via email. We also encourage anyone with any questions about our software or anything from this presentation to email us at support@optiwave.com. We appreciate you attending this webinar. Have a good day, everyone.